Okay, thank you for watching our review for our oceanography test. Yes, I guess you can think of the test as organized into some different headings. Hopefully you saw those on our review sheet. Yes, understanding respiration. What you need to know, I guess, is that obviously animals take in oxygen and we give off carbon dioxide. Really, even underwater, we think of it as so foreign that take in air, take in gas from under the water, but actually the way it works, I mean, this counter current exchange is what happens with gills. If you remember seeing our gills in our squid. Ugh. But really, as the blood flows in one direction, the current of the water flows in the opposite direction, and really the oxygen just diffuses from the water into the blood. Um, In some ways, you can almost make the argument it's more efficient than what we're doing. I mean, because we're trying to get the oxygen out of the air and into our blood and into solution. In some ways, it almost saves a step energy-wise just to take it from one solution into another. And in fact, this is really how you could think of it, how our air, our oxygen is delivered to all of our cells, our muscle cells, our brain cells. Um, we get oxygen delivered, it burns in the presence of sugar, in the presence of carbon to give off carbon dioxide and water. Energy is also given off, and that's that energy that keeps animals alive. But yes, we take in oxygen, give off carbon dioxide. It can diffuse out of the water and into the blood of animals through their gills. That carbon dioxide that the animals give off, that is what plants take in. Um, in some ways, this seems like a simple enough reaction, but if I were to just breathe into a cup of water, I would not make food. I would not make oxygen. Um, if I did, I mean, you really make the argument all problems in the world would be solved if people had a readily supply of food just from their own air. But anyway, okay. So photosynthesis is plants take in the carbon dioxide, they give off oxygen, and energy is needed, energy is a reactant, and all this energy ultimately comes from the sun to make that happen. But yes, the plants are giving off oxygen, taking in CO2. Okay, why do we really care about this? Well, really, this whole circle, that whole cycle affects the pH of the water. I don't know, if you think of the water, I guess the water in the cabbage was like this kind of reddish, purplish color. That's pretty neutral, really. We kind of say that's pH 7. As we burn things up, here's some charcoal here. Remember trying to light some wax and paper and stuff on fire in our jars. The cabbage juice would change color as smoke built up inside there, but really that smoke is just burning. I mean, we were burning carbon, burning materials with carbon in the presence of oxygen. The smoke you could think of had a lot of carbon dioxide in there. That carbon dioxide building up in the jar would make our cabbage change color. We could stick some aquarium plants, back in the jar, and that would make the color kind of come back to normal as the plants took the CO2 out of the water. Any kind of fruit juice is really what a pH indicator is. We also use some bromethymol blue, some universal indicators. But really these fruit juices that change color is how we measure pH. Okay, so what does this affect our class? Well, the idea that burning that stuff up can make carbon dioxide. That carbon dioxide can get into the atmosphere. It can settle into the ocean. Plants can take the carbon dioxide out of the water and also out of the air. But the idea is if you remove the major predator, like the sharks, really ultimately what does that do to all these food webs and food chains? If you remove the shark, there's less of the smaller animals. Fewer smaller animals really means more fish, you remove the sharks, there's more smaller animals, which leads to more animals feeding on plants. There's less plants when you remove remove the top predator. Less producers means that the pH of the ocean is going down, or the carbon dioxide building up in the ocean causes the pH to go down. And I guess how do we see that? How do we notice that? Just color changes in the plant materials is one way to monitor that pH. There are natural burning, natural volcanoes and stuff under the water that are also a source of CO2, but also a lot of our own activity of burning up things with carbon allows CO2 to get into the ocean as well. So question here, see if you understand really kind of how we describe pH. You know, we may have had some pHs too, some of the stuff we were playing with. A lot of the stuff we were playing with, a lot of the acids got to 3, 4, and 5 range, even 6. So let's say we had 1% acid. So if you want to think of it like your whole solution, 1% carbon dioxide, for our purposes, is a fair way to think of it. A 1% solution is a 1/100th. 1/100th is 10 to the minus 2. The pH describes that exponent. So as your acid gets less and less and less and less concentrated, your pH increases. Okay. Another big measurement that we focused on was pressure. Really, pressure is just pushing down on something. Pushing on the scale is pressure. We didn't necessarily push on the scale, but we pushed on these little syringes here that was hooked up to our gas pressure sensors. And we could get a whole bunch of ways to measure or monitor those pressures there, like PSI, atmospheres were some ways. But really, all of our questions about pressure, it seems silly, but you can almost answer them in thinking about a bottle of soda, because it really is water and there's gas and it's pressurized. And what would happen to this container if you started manipulating pressures and temperatures and solubilities of the gas that's in there? So how did we measure pressure? Well, yes, we used the gas pressure sensors. Why do we really care? Well, first of all, I'm fascinated by just how much pressure occurs in the ocean. This 300 times our normal pressure. I mean, that would crush. To me, it's bizarre that things actually live under these kinds of pressures and are still able to take in oxygen, still able to breathe. I just don't understand how they're not crushed and how they're actually able to function at such great depths. To me, that's fascinating. How can you the things you need to stay alive, respiration, taking in air, letting that air dissolve in there and be delivered to all your muscle tissue so you can stay alive. How does that happen at such great pressures at these big, big, deep areas of the ocean? So yes, 25 times our normal room pressure. Remember, room pressure is about 1, most people remember. But yes, the pressure as you go down in the ocean really, really climbs. Some direct relationships I'd like you to be familiar with, where the one variable goes up, the other variable also goes up. They go up together. That's a direct relationship. But yes, I want you to be able to look at a graph, look at the title of a graph, and know that pressure is on the Y, temperature on the X. Those would both go up together. But yes, think of your sodas. If you started to cook a bottle of soda, the pressure inside there would build. How much gas can you put in there? In other words, how much air can you force into those solutions? Well, these bottles are hard to squeeze. Think back to when you guys were squeezing on these syringes here and checking measuring the volumes. As you pushed on that syringe, and as you pushed harder and harder, it's just like pushing harder and harder on the scale, the pressure would go up, but the volume would get smaller and smaller inside there. So anyway, as you push on this, you can push more air into that solution. The solubility of the gas goes up as you push on that. So it's another direct relationship. But pressure on the Y, solubility on the X. Some inverse relationships we looked at with pressure. if you get hot, if this starts to get hot, so if you're checking the temperature, so here we were kind of sticking thermometers and different things, looking at temperatures. If this got hot, the air would want to come out. The gas that's dissolved inside there would want to come out. So that's an inverse relationship. Temperature goes up, the solubility, or the percentage of gas, the concentration of gas in that solution goes down. We get this shape on a graph if it's inverse. And same thing here, going back to the beginning, pushing on that syringe. It gets smaller and smaller. As it gets smaller and smaller, the pressure goes up. So we see that inverse relationship there. Okay, some other graphs we started to look at were graphs of wave functions. Now, representing a wave function on a graph, our horizontal, our x, just becomes time, and our y-axis becomes distance. So with waves, I mean, hopefully you kind of remember, we spent a day kind of looking at these tables in our book, one from down near where we launched space shuttles at Cape Canaveral in Florida, another military base here in Hawaii, and then another military base down in Mississippi. But what we tried to indicate is that the position of the moon, not necessarily the phase of the moon, not what it looks like, but really where is it relative to these areas on the Earth. If the moon was like down here on March 7th, it's an exaggerated picture, but it pulls the water towards the moon, which is really kind of bizarre and strange. Gravity is just very weird the more you study it and think about it. But the idea that the water's kind of pulled more, it seems weird to me, but that's really what causes the waves and the tides. So here, if you see the moon down here, this is a bigger stretch of water in Hawaii, down near Pearl Harbor, but a smaller stretch of water there at Port Canaveral or in Mississippi. So here then, towards the middle of the month more, the moon moves. Woo-hoo, and here's the moon relative. This is kind of looking down from the North Pole. But here's the moon, where there's a bigger stretch of water here in Mississippi and Florida, and a smaller stretch of water down there in Florida. But anyway, as that water rises, and the level of the tides change, we can keep track of that really just by putting a stake on the beach and just walking out and looking at how the water bobs up and down. We can measure those feet every day and kind of get this kind of pattern created on a graph. The other thing I want you to understand with waves and tides is how to multiply frequencies and wavelengths. You know, just how often the wave bobs up and down is the frequency. The distance of a full wave is the wavelength. But if you can multiply frequencies and wavelength, that tells you how fast the wave is moving. For tsunami warning systems to work, you would take that distance to the shore from that buoy that was bobbing up and down, detecting those measurements. And then, it's just like driving a car. How long is it going to take to get there? Well, how far away is it divided by how fast you're going. So hopefully that looks familiar too. But once again, those bobbing buoys really do just kind of save lives because they can give people time to evacuate and get to higher ground if it was a tsunami or an earthquake under the ocean. Okay, now another thing, if we were trying to do waves with light, it's really a completely different concept than ocean water bobbing up and down. But the thing is, ocean water bobbing up and down, we can also represent light on that same kind of graph and get the same kind of pattern going. It's still time on our x. It's still distance on our y, but this thing with light, now it's not days or feet. It's like split seconds can be our increments of time. The distances become not even just centimeters or millimeters, things like nanometers, very, very small distances. But yet the pattern on a graph could be made to look the same depending on how you scale it. So this thing with describing light in terms of frequencies and wavelength really is just a function of what the graph looks like. But another way to think of it, to get things to glow, to get things to give off light, we move electricity. or we burn things for that matter. When things burn, when things glow, when electricity moves, it moves back and forth. And if the electricity moves back and forth in these certain amount of spaces, these distances, that represents the type of energy that's created, the type of radiation that's created. So if you think of your cell phones or our Wi-Fi signals, that pieces of electricity are bouncing around in like this centimeter, back and forth in this little center. And our nerve endings, the sensors in our nerve endings, pick up this visible light. So this is really where biology interacts with this type of radiation, this type of energy. We really don't sense or detect or interact with radio waves, Wi-Fi signals, remote controls and scanners, radio waves, an antenna, an old-fashioned TV antenna. But yet our cells are able to sense visible light. And that's just these spaces, these nanometer distances represent the distances between the atoms and molecules in our brain cells and our optic nerve that pick up that. So wavelength is really just the distance that the electricity is bouncing back and forth in. Our bodies can pick it up in this visible range here. Our bodies can also interact with ultraviolet light, X-rays, gamma rays. These can do damage to you, and they, in fact, can affect even more than just nerves and cause signals in your brain to fire. These things, like I said, these types of radiation can cause damage if they build up and you're exposed to them over time. So it's weird to think of light in terms of wavelengths, but it's really just a way to describe how we sense or detect things that glow and burn and give off the light. If we were to use our spectrophotometer, it would have 400 nanometers of light filling up the inside of this box. You dial in that wavelength there. You're dialing in like purple light, or like these purple filters would slide into place and fill the inside of that box up with purple light. And then the sensor really could just pick up how much light can move through, how much light can be absorbed for that certain color. Okay. So why do we care about that? Well, really the way we determine what's in water is by shining light through it and looking at how it interacts with the light. And every unique material has what's called an absorption spectrum, or its own unique pattern of how it absorbs wavelengths of light. We can look at that percentage of light absorbed on the Y versus the color versus the wavelength on the X and create a graph. And every solution, every unique substance would have its own unique pattern. For what we did, we just said, okay, what color is this solution A? Well, if that minimum absorption, that minimum percentage of light absorbed is around 600, that's probably like this orange-yellow type solution. That's the color of light that gets through. That's the color of light that you see, that you detect. Solution C here, this one has a minimum between 700 and 800. The minimum right around here, this would probably be a red solution. Okay, so the color you see is the color that is not absorbed, the color that gets through. Okay, so why is that significant? Well, we've looked at some graphs of how light would penetrate the ocean water in different depths. So the question really is why is the ocean blue? Well, if you were to look at a percentage absorbance versus wavelength for ocean water, we would see that it does not absorb the blue. So we looked at some charts where it showed how the light penetrated different levels of the water. Blue tends to be the one smallest absorbed. The ocean water does absorb a lot of these other colors. Okay. Now another thing with this, what we could do is measure the percentage of light that does get through, the percent transmittance. And the idea is the darker and darker our dye was, the darker and darker these test tubes were, the more and more the dye was concentrated, the less light that we would see transmitted through there. So we got this inverse relationship on that graph as well. But really, the thing I'm hoping you can kind of see from peeking at this type of graph and from peeking at this type of graph, this is how we figure out what's in stuff. If we don't know what water has in it, we see how it interacts with light. Not only can we start to identify what molecules are in there based on its absorbencies, but we can also detect how much of that chemical would be in there, what its concentration would be. And it's all relative to a standard. If you guys remember, we had to always be zeroing these. We just used tap water to zero it with, but that was kind of our standard, our zero mark. But yeah, not only is ocean water tested this way, but so is like bodily fluids, urine, blood, figure out what's in there. And finally, there is a map ID portion on the test. If you remember, I guess going way back, we watched Kon-Tiki, how they sailed from South America. They did sail past the Galapagos and into Polynesia. It was kind of like, how could someone sail across the ocean before Columbus? I thought that was an interesting story. It was a true story of how people really did it in the early 1900s to try to replicate that journey that the native South Americans took to Polynesia. We watched shark water, how the overkilling of sharks is starting to affect the ecology of the world. And it was the idea that the killing of sharks, more fish, less plants, the ocean water is slowly becoming more acidic, or there's more carbon dioxide in it. But shark water did a lot of filming around the Galapagos Islands as well. We looked at tidal data from Florida. We looked at tide data from Hawaii. We also looked, here's the Mississippi River, so right here in Mississippi. We looked at tide patterns there as well. We also watched some footage from the 2004 tsunami. Really, we didn't have enough warning systems in place then. The places where there was the most loss of life was here in Indonesia, and then just north here in Thailand as well. But once again, so hopefully you've kind of gone through the test review and tried a lot of the practice, but a couple questions about respiration, animals using oxygen, giving off carbon dioxide. Plants take in that carbon dioxide. pH, how do we measure it? Color changes. Can we monitor those color changes using a spectrophotometer? You bet. In fact, a lot of times we'll add indicators to solutions and then go through and run a spectral analysis to see what types of stuff are in there. But yes, what does burning do? Burning ends up lowering the pH or adding carbon dioxide to those solutions. What do plants do? Plants end up making it closer to water, closer to neutral, less acidic, end up allowing that pH to climb as the carbon dioxide comes, or as the carbon dioxide is not allowed to build up in the water. So once again, the pH, as you get closer to water, really this is, a lot of times we say our tap water is about 7, our blood or so is about 7. Just the cabbage just plucked out of the ground, that purplish kind of red color of the cabbage, just regular water made it this color. But then we could add different salts, change the pH, even just heating it changes the pH too. Okay. So then, yeah, once again, we played around with pressure. Just think of pressure as just force, weight of the air. Atmospheres, PSIs, those are great ways to measure pressure. And then all those different ways to think of those direct relationships with pressure. But once again, I'm hoping if you think of a soda, it's kind of common sense. Those inverse relationships that we looked at with pressure. How can we get a wave pattern on a graph? Time on the X, distance on the Y. Just watch things bob up and down. We can get that same wave pattern on a graph for light, just in different units of time, smaller units of distance, but still the same pattern to just try to describe light. And the relationships with light I want you to be familiar with are be able to identify those minimum absorbencies and be able to identify this inverse relationship as the concentration of your stuff in there increases, your percentage of light that goes through decreases. And then hopefully it's an easy map. A few states, Florida, Mississippi, Hawaii, Galapagos Islands down here near South America, and then Indonesia and Thailand. But thanks for your attention. Good luck.